So if the index matches a number of factors in the radical, then we can convert from entire radicals to mixed radicals. So for example, if we have square roots, if we want to deal with square roots, we're dealing with powers of 2. So it's going to be all these ones in here. And to do square roots, we need to know our powers of 2, so we can undo those powers of 2. So for example, 2 squared is 4, so if we have 4 inside the radical, we're able to square root and get the 2. If we have 49, we can square root to get the 7. So to be able to, this is what it means so that the index matches a number of factors. So we have to have, if we have a cube root, okay, when we're talking about cube roots then, we're talking about perfect powers of 3. So we're talking about these numbers here. And these cube roots have 3 factors that are the same, in which we are then able to take those factors out of the root. So an example would be if I had 27 times 2, the 27 is a perfect cube factor. Okay, if I have an index of 3, I can undo that perfect cube of 27 and get 3 on the outside and leaving the 2 on the inside. Okay. So we need to know some of our perfect powers because we need to be able to do this without a calculator. So this chart gives you an idea of the powers that you would need to know. You really should know all your powers of 2 up to at least 13. Our powers of 3, we probably should know up to at least 125. Our powers of 4, we should know at least up to 3 to the power 4. Powers of 2, okay, or fifth powers, we should know 2 to the power 5, 2 to the power 6. And that's about all you would really need to be expected to know. The other ones we would probably allow you to use a calculator for those. But those ones on the chart, it's good to know these ones so that we can do these efficiently and without a calculator. So if we want to do these ones, what we do is look at the index first. I have an index of 3. And so what I'm looking for is perfect powers of 3. And when I look at 8, 8 happens to be a perfect power of 3. So I can just undo this power of 3 with the cube root. So this is 2 cubed. And so the cube root and cube undo each other. So we're just left with 2. Here we have square roots. Okay, so we look for perfect square factors. So when I write this as a perfect square factor, I can find a perfect square of 25 times 2. The perfect square of 25 can then be square rooted, and that gives us 5, and it leaves the square root 2 in. And since this is multiplication, it's still going to remain multiplication on the outside. So looking at the index 3, we need to find our powers of 3. So our powers of 3 would be, well, 2 cubed was 3. That's divisible into 24. So then what I can do is I can factor out that power of 3. And that's going to be, power of 2. So it's going to be 2 cubed is 8 times 3. So this becomes 2 to the power of 3 times 3. The 2 to the power 3 and the cube root undo each other, and we're left with the cube root of just the 3 inside. Okay, so then looking at this next one here, it's an index of 4. The powers of 4 we're not super familiar with, but we only really need to know 2 to the power 4 or 3 to the power 4. And so if we look at the powers of 4, yeah, it looks like 16 is divisible into 32. So when I rewrite this, I'm going to have my perfect power of 4 factor. Okay, so it's going to look like that. This is really, in fact, going to end up being 2 to the power 4 times 1, 2 to the power, times 2, which gives us 2 to the power 5. Well, only the power 4 can come out. So we end up with fourth root and power 4 undo each other. And then we're left with the 2 inside the root. So this 2 is this 2 here. This next one here, we're dealing with powers of 2 since it's a square root, so we can find our perfect square factors. 9 times 2. Okay, the square root of 9 is going to be 3. That comes out on the outside. The square root 2 remains on the inside. And again, it's times here. So this is times here. Okay, this means 3 groups of square root 2. For 54, our perfect cube factor is going to be 3 cubed times 2. And again, the 3 cubed ends up on the outside. The cube root and cube undo each other. We're left with 3. We have an index of 3. And inside that square root, we have the value of 2. So that is starting with the whole entire radical and making it into a mixed radical. We can do the opposite. So in this case here, we pulled out the 2 on the outside. So we basically did the 4th root of 2 to the power of 4. The opposite can be done. If we have a number on the inside, we can put that 2 inside as 2 to the power of 4. So this is how we're going to approach making an entire radical. We're going to take our square root 7 and we're going to make this 2 into 2 squared square root. Okay, which is the same as 2. Now, since they are the same index here, we can put them all under the one radical. So it just becomes basically, we don't have to show this step necessarily. I just want to show what's going on. We're basically putting the 2 into the square root by squaring it. And then working that out, we end up with 2 squared is 4 times 7, and I end up with 28 as my entire radical. So same thing here. I'm going to skip the first step, and I'm going to just show the 10 inside the square root as 10 squared. And I can see that 10 and square root of 10 squared are really the same thing. Okay, so I've just rewritten the same thing in a different way. Now it's inside the square root, and I can apply it with multiplication onto the value of 30, which is inside the square root. So this becomes 100 times 30, so we end up with 3,000. So applying the same process, we have an index of 3. To go from outside to inside, we need to cube it. Okay, and again, make note that we haven't changed the value of anything. That's important because math is about keeping track of these values. We've cubed and cube rooted. Yeah, that's the same as 4. And inside, we have the 3, so we have a times 3. So 3 to the power of 4 is 64. So we end up with 64 times 3. So that works out to be 192 inside the cube root. Okay, and this factor of 64 comes from 4 on the outside, becomes 4 cubed on the inside, and that ends up being 64.